Hello, welcome back to the channel where we are reviewing the principles and practices of commercial construction textbook. So this video is dedicated to chapter 7, and that is all about concrete work. So the extensive use of concrete is ample proof of its outstanding characteristics as a building material. It is such a familiar material that we take for granted the remarkable process of which cement and water mixed with a wide range of aggregate materials are converted into a strong and durable material of almost any desired shape. The development of modern Portland cements can set quickly even underwater began over 100 years ago when the raw materials and processes needed for their manufacture were first recognized. Today, hundreds of scientists, engineers, and technicians are engaged in studying these materials, attempting to understand and to improve them further. So let's talk about some organizations that are dealing with the codes and standards, and those are the Portland Cement Association, the American Society for Testing and Materials, or ASTM, and the American Concrete Institute, or ACI. So let's move to the first subchapter, and that is the aggregates for concrete. So concrete is the product of a combination of Portland cement and water paste with some type of aggregate. The paste surrounds the aggregate particles and its sets, return to a limestone-like state, binds them solidly together. At the same time, to form a dense concrete, the paste must fill the voids between the particles of the aggregate. So it is desirable to use a maximum amount of aggregate when making concrete of any given stress for a number of reasons. In the first place, cement is up to 10 times more costly than aggregates. Second, cement paste tend to shrink while setting and curing. Consequently, the use of more paste than is necessary results in a more expensive concrete and also produces excessive shrinking. So aggregates used for concrete mixes are generally placed into four classifications. Those are sand, gravel, crushed stones or natural aggregates, and air-cooled blast furnace slag that are used to produce normal weight concrete with a unit density ranging from 135 to 160 pounds per cubic foot. Materials such as expanded shale, slate, clay, and slag produce a structural lightweight concrete with a density of 85 to 115 pounds per cubic foot. Lightweight materials such as vermiculite, perlite, pumice, scoria, and diatomite are used to produce non-structural insulating concrete with a density ranging from 15 to 90 pounds per cubic foot. Heavy materials such as hematite, barite, limonite, magnetite, steel punchings, and shot produce heavyweight concrete with a unit density of 189 to 380 pounds per cubic foot. The aggregates used in making concrete usually occupy 60 to 80% of the total volume. As a result, the type and quality of the aggregates have a major influence on the on the properties of concrete. It is important to know as much as possible about the aggregates being used to be able to produce concrete to required specifications. Natural aggregates are divided into two classes. Those are fine and coarse aggregates. So fine aggregates include material that does not exceed a quarter-inch diameter. And the coarse ones normally range from 3/8 to 3 inches in diameter. Soundness. So concrete can only be as strong as the aggregate from which it is made, and aggregate, particularly coarse aggregate, should be inspected to see that it does not contain weak or laminated particles, soft and porous particles, or bits of shale. Aggregate soundness may also be determined by its abrasion resistance, which is of particular importance when the concrete is to be used for heavy-duty floors. Then cleanliness. Sealed clinging to the surface of coarse aggregate prevents proper bonding of the cement paste. In fine aggregate, the presence of too much fine material means a significant increase in the surface area to be covered with paste, resulting in either having to use more paste or in the thinning out of that in use. Silt test. The presence of silt in coarse aggregates can usually be detected visually, or in case of fine aggregates, a silt test is used to determine the amount of very fine material present. To conduct a silt test, you can do the following. You can place 2 inches of fine aggregates to be tested in a standard 1/4 or like 1 liter glass jar, and then fill the jar 3/4 full of water, replace the cover and shake well. Let the jar stand for several hours until the water has cleared. Upon settling, the fine silt will form a layer on top of the sand. If this layer exceeds 1/8 of an inch or 3 millimeters depth, the aggregate is unfit for making good concrete unless part of this material is removed. Then colorimetric test. So the presence of small amounts of fine organic matter in the cement paste retards its setting action, sometimes so much that a mix will dry out before setting properly. So, the presence of harmful amounts of organic matter in fine aggregates need to be tested as well. So gradation. The proper gradation of particle sizes in the aggregate used to make concrete is essential for a number of reasons. It is apparent that the fewer the number of pieces required to fill a given volume, the smaller total surface area will be. So this can be demonstrated with the cubes or spheres, and you can see there is the illustration here in the textbook. So we are moving to the next subsection, and you can see there are pictures here of well-graded aggregate. You can see them how we can actually reduce voids by improving gradation. And we're moving to the fineness modulus test. So when doing a fineness modulus test on fine aggregate, you can use the set of 6 standard wire screens. So, and that will actually show different openings per square inch. So, from a dry quantity of the fine aggregate to be tested, very carefully weight the certain amount of material and place the sample in the top sieve, and then it goes all the way down, and each grade is treated the same way. So fineness modulus numbers for fine aggregates should range from 2.3 to 3.1, and any fine aggregate with a fineness modulus number falling within this range will generally be suitable concrete aggregate from a gradation standpoint. So the the fineness modulus is not an indication of whether the proper amount of each grade of sand is in the sample. For a great number of gradients will give the same value for fineness modulus. It can be determined from the results of the test whether the sample contains the right proportion of each grade of sand. So, and please see the graphic representation of sieve analysis, how that is done. And we're moving to the moisture content and absorption. So for concrete mixes, both fine and coarse aggregates are considered to be a saturated surface dry condition at the time of introduction into the mix. If the if the aggregates are not in this condition, then the amount of water required for the design must be adjusted based on the absorption of the aggregate and its moisture content at the time of mixing. Another reason to determine the moisture content of the aggregates, particularly the fine aggregate, is that when water is present in certain proportions, a phenomenon known as bulking can occur. So the amount of bulking varies with the fineness of the sand and the amount of moisture present. By mass, 5 to 6% water will produce maximum bulking, and the amount of bulking is more pronounced in fine sand than in coarse sand. So again, there is a sand bulking chart. Please refer to that. And there is also fineness modulus test for sand. Specific gravity of an aggregate is the ratio of its mass to the mass of an equal volume of water. It's not a measure of aggregate quality, but it's used in making calculations involved in mix design, particularly those concerning absolute volume. There are a few methods to actually determine the specific gravity. When we talk about the particle shape and surface texture, um, they can have an effect on the properties of fresh concrete. So rough surfaced and long, thin, flat particles require more water to produce workable concrete than the rounded or cube-shaped ones. So long, thin, or flat particles have more relative surface area and therefore need more cement paste to cover the surface. In order to maintain the same water-cement ratio, it is therefore necessary to use more cement, which is obviously more expensive. So we are moving to the next part, and that is Portland cement. So the chemical reaction that is produced when cement is mixed with water is known as hydration. When the cement paste is mixed with aggregates and allowed to cure, the result is a very hard and durable substance. The raw materials used in the manufacture of Portland cement are lime, silica, alumina, and iron. These materials are readily available from natural deposits. From these basic materials, four principal compounds make up the composition of cement. By varying the proportions of these basic components, the properties of the cement can be modified to best suit a particular application. So there are 5 basic types of cement that are available. Type 1 or normal cement, used as a general purpose cement, the properties of other cement types are compared to type 1 for relative differences. Type 2 or moderate cement, used where projection against moderate potential surface attack is required, potential sulfate attack is required. It can also be used in large mass concrete structures as it produces less heat during the hydration process. This cement type also gains strength at a slower rate than type 1 cement. Type 3, or high early strength, used where high concrete strength are required in a very short period of time. This cement produces comparably higher heat of hydration than type 1 cement. Type 4, or low heat of hydration, used where the heat of hydration must be kept to a minimum, used in massive concrete structures such as dams. Type 5, or sulfate resisting, used where the concrete will be exposed to severe sulfate attack, normally used in concrete foundations where high sulfate soils or groundwater is present. And this is something to memorize, so I highly recommend to create a little chart and learn that. So cement is usually gray in color, but can also be white. Coloring may be added to white cement for specific effects. Cement is transported in bulk for large projects or in ready-mix plant production or of concrete. It is transported in bags when smaller quantities are required. In the US, a standard bag of cement weighs 94 pounds. And in Canada, for example, the mass is 40 kilograms or 88 pounds. We are moving to the next subchapter, which is the concrete mix design. So, concrete is a very versatile material and has been adapted to many uses. Since there are no equations that will accurately predict all the properties necessary for a given concrete mix, the design formulas are empirically derived. Each variation of a concrete mix begins with a trial batch using a relatively small quantity of materials. The basic mix consists of three principal ingredients: water, cement, and aggregates. Each of these materials plays an important part in determining the quality of the mix. Although the compressive strength is the leading indicator for a concrete mix, other properties are equally important. So let's take a look at the water-cement ratio. The concrete mix design is based on the theory that the strength of the concrete is regulated by the amount of water used per unit of cement, provided that the mix is plastic and workable. This is water cement ratio theory, or Abram's law, which says that the amount of water used per pound of cement is increased, the strength of the concrete will decrease. So please take a look at the chart here. You can see the compressive strength for various water cement ratios, and you don't have to memorize it. It's something just to refer to. So concrete mix design is also based on the assumption that sound coarse aggregate is essential to the production of high quality concrete. This being so, the best concrete is produced by using the largest size of aggregate and the greatest appropriate proportional quantity of it per given volume of concrete that is compatible with job requirements. Again, there is a chart showing volumes of coarse aggregate in cubic feet per cubic yard of concrete. Then again, there are recommended maximum sizes of aggregate for various types of construction. So, for example, in designing concrete mixes, it is in the desired consistency of the plastic concrete. Consistency has a twofold meaning. It means the plasticity or flowability of the mix, but can also refer to the batch-to-batch variation in the concrete mix. So the both are indicated by the slump of the concrete. The slump is measured with a slump cone using a particular test method and will be described in tests on concrete later, so we'll talk about that. But here you can see the recommended slumps for various types of construction. And you can see the size of the slump in inches and millimeters. So when we talk about the absolute volume method, we need to understand that concrete is made by binding together aggregates with cement paste in such a way as to produce a strong, relatively impervious material containing no voids in its bulk. In other words, a given quantity of concrete is made up of solid material. Theoretically, no air spaces are involved. This product is made by mixing 4 basic ingredients, only one of which, and that is water, contains no voids. So the other 3 are made up of particles that have air spaces in and between. So, and consequently, in a given volume of any of these, only part is actually usable. The part of the given volume that is actually cement or stone is known as the absolute volume, so volume without any voids. And there is a formula to calculate that. So please just review the calculations and then the problems and the solutions. So that is important to know before you do that. So trial mix method. An alternative method of designing a concrete mix is to use the suggested trial mixes shown in the table, and you have that table in the textbook. It's quite likely that having made a trial batch from amounts given in one of the tables, some adjustments will still have to be made to produce the desired slump. So when making a trial batch, enough water should be added to produce the desired slump, whether that is the amount of water given in the table. So again, it's not something to memorize, it's just for your reference. And also you can see the suggested trial mixes for non-air entrained concrete of medium consistency. So you can see that too. And there are a couple of problems to solve. So when we talk about concrete admixtures, ordinary concrete consisting of Portland cement, water, and aggregates, although very useful, was found to be lacking in durability when exposed to cycle of freezing and thawing. Efforts to make its useful lifespan led researchers to discover that a concrete mix containing a small percentage of entrained air had much better resistance to the effects of freeze-thaw cycles than an ordinary concrete mix. Entrained air is very finely divided spherical voids consistently dispersed throughout the cement paste. Very quickly, air-entrained concrete became the standard for structural applications where both durability and strength were a concern. In addition to an increase in durability, it was found that the addition of a small amount of air entraining agent produced a more fluid concrete mix, thereby reducing the amount of water that had to be used in the mix design. So there are some common admixtures and their effects, and let's take a look at them. So the first one is accelerators. Chloride type and non-chloride type improve the setting time and early strength gain. Then the second one is air entraining admixtures that improve the durability and workability of the concrete mix. Another one, coloring agents can provide different colors for concrete. Then pumping additives improve the pumpability of concrete. And those can be organic polymers, organic bentonite and natural porcelain, fly ash, and hydrated lime. So those are one of the typical admixtures. Retarders increase the setting time of a concrete mix by slowing the initial set of the cement. This slowing provides a more homogeneous integration of concrete placed in lifts or layers, reducing the formation of cold joints within structures such as a wall or deep girder. Superplasticizers increase concrete flow and retard the setting time. Because flow is increased, the quantity of the water in the mix can be reduced. Water reducers reduce the quantity of water required in the mix. So some additives to concrete can also be used to replace part of the Portland cement in the mix. And this can be important for several reasons, including lowering the cost of the mix and providing a reduction in the alkali content that can be particularly beneficial in areas where aggregates are known to experience alkali silica reaction in the concrete. The most common additives used for this purpose is fly ash. Additionally, another type of cement known as ground granulator blast furnace slag cement, or GGBFS, may be used as partial replacement in many concrete mixes. So let's move to the high strength concrete section. The term high strength concrete is applied to mixes that achieve strength of 6,000 psi or higher. Strengths of as high as 20,000 psi can be achieved with the proper selection of materials and with strict quality control. So during the mix design stage, the final selection and proportioning of all materials can be used in the mix that will depend on the required design strength of the concrete. When we add cementing materials to the concrete mix, such as silica fume or fly ash, that enhances the strength of the cement paste. This must be done with care to ensure this actual production volumes of concrete maintain the desired strength, durability, and volume stability. So the selection of aggregates for high-strength concrete is as critical as the selection of the cementing materials. It has been found that crushed rock aggregates provide better result than gravel aggregates due to their rough angular shapes. Coarse aggregates may need to be washed to achieve good bond between the cementitious paste and the aggregates, and the maximum aggregate size ranging from 3/8 to 9/16 of an inch provide excellent strength characteristics to the mix. Admixtures such as superplasticizers to improve workability and keep the water cementitious materials ratio to a practical minimum are highly recommended. And it's always best to have a consultation with a concrete mix supplier. Area training of high strength concrete for protected sections is not necessary. However, entrained air is a must for exposed structures and structures exposed to freeze-thaw cycles. Placing of high strength concrete on the construction site must be done as quickly as possible. Adjustments made to the concrete mix at the site must be done under the supervision of qualified personnel, fully knowledgeable of the properties of high-strength concrete. The arbitrary changing of water-cement ratio can produce really bad consequences. Delays between lifts during the placing of the concrete must be avoided, and quantities delivered to the site must match the rate of placement. Consolidation of the concrete must be done quickly and thoroughly. Because high strength concrete is usually relatively stiff, under consolidation can be a problem. Proper curing cannot be overemphasized. Adequate moisture and moderate temperature must be maintained for an appropriate length of time to ensure the desired strength. This is particularly important when 56 and 90-day strengths are specified. So, and we're moving to the use of fast setting cements. And it is sometimes necessary to use concrete in situations when it's impossible to wait the required period for concrete made with normal Portland cement to set and strengthen. In these situations, it's possible to use high early strength Portland cement. And you can see that um, there are different charts showing early strength of normal Portland and high early strength cements. So for the normal one, you can see that it's 1 day, 3 days, 7 days, and 28 days. And for the high early strength Portland cement, you can see 1 day, 3 day, and 7 days actually is for 4,000 psi. So again, another chart showing the effect of temperature on the strength of concrete, and there's nothing to memorize, just for your future reference. So tests on concrete. Let's talk a little bit about that. To ensure consistent results from concrete mixes, especially under site conditions, standard tests are performed on concrete samples taken at predetermined intervals from concrete batches as they arrive at the site. So, and there are standard procedures that are provided by ASTM, and those testing are required. So typically, as the concrete arrives on the site, the fluid concrete is checked for slump and the percentage of entrained air within the mix. The air content may be measured by using ASTM C173 method, that's the volumetric method, or ASTM standard C231, that's the pressure method. The pressure method is often favored by technicians in that it can be done quickly on the site and it provides reliable results. So additional samples of concrete are taken from the batch in the form of standard test cylinders. The number of cylinders to be taken for the compressive strength testing should be outlined in the specs along with the appropriate reference standards. So the official measure of compressive strength in accordance with ACI 318 building code requirements for structural concrete is to test two 6-inch diameter by 12-inch high specimens at 28 days and take the average of the two results to report the compressive strength. Additional specimens and other testing intervals may be chosen depending on the project requirements. So a slump test, that's ASTM C143, is made to check that the concrete has the flowability required for placing and to check the consistency of the concrete from batch to batch, given the same mix design. A compression test, that's ASTM C39, is made to determine the strength of the cured concrete and to see that it meets the design specifications after having been sampled, cured, and tested under standardized conditions. So in order that concrete may demonstrate the quality, it must be allowed time to gain strength to cure. In most commonly used mixed design applications, concrete is assumed to have gained its full design strength within 28 days under ideal curing conditions, and that period is taken as a standard for testing purposes. But experience has shown that concrete cured under ideal conditions exhibit an age-strength relationship. Specimens tested at time intervals of other than 28 days will generally fall into predictable strength ranges based the 28-day strength. So And those takes usually taken at other times, 1, 3, or 7 days, and that will accordingly show meaningful indications as to what strength can be expected at 28 days. So, when preparing trial batches in the lab, the 6-inch by 12-inch test cylinder is filled in 3 equal layers, each layer having been tamped 25 times with the standard tamping rod. And you can see here is the how people fill the test cylinder. So in many authority having jurisdictions or AJ will allow the use of reusable caps made of stainless steel and having a replaceable neoprene contact liner for the test. So again, a few pictures here, please refer to them. You can see the concrete test cylinder ready for loading, and you can see the cap and concrete test samples. That's how it's brought to the lab. So we are moving to the preparation for placing concrete, what needs to be done. So before placing concrete, the subgrade must be properly prepared and forms and reinforcing must be erected according to specifications. Subgrades must be trimmed to specific elevation and thoroughly compacted and should be moist when the concrete is placed. A moist subgrade is particularly important to prevent overly rapid extraction of water from concrete that work, such as floors and pavements, particularly when the concrete is being placed in hot weather. Again, please see the images. You can see the way the subgrade is compacted and prepared for the concrete pour. So when fresh concrete is to be placed on hardened concrete, it's important to secure a good bond and a watertight joint. The hardened concrete must be fairly level, rough, clean, and moist. Some of the aggregate particles must be exposed by cutting away part of the existing surface by sandblasting, by clearing with hydrochloric acid, or by using a wire brush. Um, so preparations must also include the building of adequate runways for wheelbarrows or buggies. Build runways be reasonably smooth and rigid enough to prevent the wheelbarrows or buggies from bouncing as they travel. Some means of transferring concrete from the wheelbarrow, buggy, or bucket into the forms must also be provided. They may consist of a baffle board, hopper, downspout, or chute. And we are moving to the mixing concrete chapter. So concrete should be mixed until it is uniform in appearance and consistency. The time required for mixing depends on the volume and stiffness of the mix, to some extent on the size of the um, uh, aggregates. So a drum mixer that consists of a rotating drum with stationary blades fixed on the inside, and that's pretty common for small applications. Then batch mixers are available in sizing from 1.5 cubic feet to 4 cubic yard capacity. For general construction works, standard mixers are rated 3.5, 6, 11, 16, and 28 cubic feet of mixed concrete. For larger projects and central mixing plants, mixers of 2 to 8 cubic yards capacity are used. So mixers may be tilting or non-tilting with either high or low loading skips. High loading skips are suitable when the skip is being charged from a bean batcher, but the low loading type is preferably if the skip has to be charged by shovel or wheelbarrow. Non-tilting mixers may be equipped with a swinging discharged chute. Many mixers are provided with timing devices so that they can be set for a given mixing period and cannot be opened until the designated mixing time is up. So mixers should not be loaded beyond their rated capacity and should not be operated at speeds other than those for which they were designed. Overloading or running either too quickly or too slowly prevents the proper mixing action from taking place. When increased output is required, a larger mixer or additional ones should be used. So, used under usual conditions, no more than approximately 10% of the mixing water should be placed in the drum before the dry materials are added. Water should then be added uniformly with the dry materials, leaving approximately 10% to be added after the dry materials are in the drum. If heated drum is used during cold weather, this sequence may have to be changed. In this case, addition of cement should be delayed until most of the aggregate and water are mixed in the drum. So this is done to prevent a flash set of the paste. A set brought about too much heat than when the water and cement combine. So countercurrent mixer, what is that? Let's take a look at that. And that is called so because of the mixing system that is employed. It consists of a horizontally revolving pan into which it suspended one or more vertical three-paddle mixing tools offset from the center of the pan. The pen rotates in a clockwise direction while the mixing tools turn counterclockwise, thus producing a high degree of agitation in the material being mixed. And please refer to the diagrams here, and they're quite interesting. So, transit mixer. A transit mixer is the most common form of production concrete mixer that is used for the construction site. That's a mobile drum mixer that mixes it as it's driven to a job site. Concrete provided under this process is called ready mixed concrete. In this process, the mix design constituents are charged by weight into the mixer. Initially, after loading the materials into the mixer, the drum is turned at mixing speed for 70 to 100 revolutions. At that point, the transit mixer proceeds to the job site with the drum uh, turning at a transit speed to keep the concrete from segregating. Just before discharge from the drum mixer, the drum speed is again increased to mixing speed for typically 20 to 30 revolutions. The concrete is then discharged from the drum mixer for final placement, and each drum mixer has a revolution counter for total revolutions, including mixing and transit, and it should not exceed 300 revolutions. The production and delivery of ready mixed concrete is outlined in ASTM C94. So when we talk about temperature and slump control, it's important that the maximum and minimum temperatures of the concrete in the mixer be controlled in all seasons. So significant temperature changes may bring about changes in water requirements, slump, or air content. So that was it for mixing concrete, and we are moving to the machinery for placing concrete. So as you already know, concrete may be mixed on the job site or brought to the site by truck from a concrete batch plant. In either case, various methods are available to the contractor to move the concrete from the mixer locations or concrete truck to the pour location. So, what can be used? Wheelbarrows and buggies. Wheelbarrow are used where concrete volumes are small and the distance from the supply location to the forms is short. So, smooth runways are required. So push carts and power buggies are made in a variety of sizes, and that is equipped with pneumatic tires for smoother operations. They can carry more concrete than the wheelbarrows, but they still require robust runways that must be sufficient width to ensure safe operating conditions. Then um, chutes may be used to carry concrete directly from mixer to forms or from a hopper conveniently situated to allow shooting. Chutes should be metal or metal lined with rounded bottoms and of sufficient size to guard against overflow. Then buckets. Buckets lifted and moved about by a crane or cable are commonly used while, um, where concrete has to be placed at a considerable height above ground level or where forms are in otherwise inaccessible locations. So, belt conveyors. Belt conveyors used to transfer concrete may be classified into three types. Those are portable, then uh, the side discharge conveyors. So series or feeder conveyors operate at fairly high belt speed, whereas the other two conveyors operate best at considerably slower speeds. And again, you can see the mobile series conveyor with drop chute, how that is operating. Pumps. Concrete pumps have enhance the placement of concrete by doing away with the need for special ramps, runways, containers, and cranes that are needed for some of the traditional methods for moving concrete on the site. So the concrete pump, complete with its own extended boom, is normally mounted on a truck equipped with outriggers to maintain stability of the truck when the boom is extended, much like a truck-mounted crane. So again, there are pictures. Please refer to them. Um, and we are moving to the concrete transportation. So when concrete is brought to the job from a mixing area some distance away, any of a number of methods may be used. They include dump trucks, transit mix trucks, agitator trucks, and rail cars. Dump trucks should have a body of special shape with rounded and sloping front and rounded bottom, and the rear end should taper to a discharge gate to facilitate delivery of the load. So please take a look at the images here. There is an image of the transit mix truck as well as the concrete batching plant. So um, the the trucks are available in different sizes, and each batch of concrete should be mixed not less than 50 or more than 100 revolutions of the drum or blades at the prescribed rate of rotation. So an agitator truck is similar to a transit mix truck, except that it carries no water tank. Rail cars specifically designed for transporting concrete are used only on large projects. So some are tilted to discharge through side or end gates, whereas others discharge through bottom gates. And you can see the graphical representation of different methods here in the book. And we are moving to the next subchapter, and that is placing concrete. So concrete must be placed as nearly as possible to its final position. It should not be placed in large quantities in one position and allowed to flow or to be worked over a long distance in the form. The mortar will tend to flow ahead of the coarser material, thus causing segregation of the coarse aggregate and sloping work planes. Concrete placed in forms must never be allowed to drop freely from more than 1 meter. When concrete must be placed into deep forms, rubber or metal chutes similar to a tremie must be lowered into the formwork to control the rate of fall of the concrete. So again, please refer to the images. You can see correct and incorrect methods of placing concrete. And also you can see the different variations of placing concrete on a sloping surface. And then you can see the correct and incorrect ways of dumping of previously placed concrete. So concrete should be placed in wall forms in relatively thin layers or lifts, and that's 12 to 18 inches deep. Each layer placed the full length of the form before the next lift is begun. So concrete being placed in columns and walls must be allowed to stand for approximately 2 hours before placing the concrete for monolithic girders, beams, and slabs. And this time allows for concrete in the walls to settle and prevents cracking. So the correct placing of concrete includes proper consolidation to ensure that no pockets or spaces remain unfilled and that the face of the formed concrete has been made as smooth as required by the specs. So you can see the electrically driven internal vibrator and then gasoline powered vibrators just to make sure that everything is smooth. And also you can see the correct and incorrect methods of consolidating concrete here. So let's talk a little bit about underwater concrete. Placing concrete underwater requires special techniques. So it cannot be dropped through the water, but must be conducted to its final position. A number of methods are used to place concrete for underwater structures, among them being the use of a tremie, an underwater bucket, a concrete pump, or pre-placed aggregate. So let's take a look at all of these. Tremie, one of the most widely used methods of placing concrete underwater is tremie. So this is a pipe with a normal diameter 8 times the maximum size of the coarse aggregate in the concrete being used, and it's commonly made in 10 and 12-inch diameters in 10-foot high lengths. So the bottom end is fitted with a watertight valve or a plug of some kind, and then the tremie is lowered into position by hoisting equipment. Placement is begun by filling the tremie with concrete while the bottom valve is closed and then opening it to allow concrete to flow out. It flows outward from the bottom of the pipe, pushing the existing concrete surface outward and upward. Concrete is fed to the tremie continuously as long as the valve is open and as long as the flow is smooth so that the concrete surface next to the water is not physically disturbed. High quality concrete will result. Here are a few images. Then there is also underwater buckets, concrete pumps, and pre-placed aggregates that can be used. Let's talk about hot weather concreting. So placing concrete during hot weather presents some special problems. And since cement hydration is a chemical reaction, high temperatures accelerate the set of concrete as this is part of the hydration process. That leaves only a short time available to place and finish the concrete. In addition, more mixing water is usually required for the same amount of slump. And if more cement is not added, also to maintain the water cement ratio, the concrete strength will be reduced. So, water may be cooled by insulating and burying the supply line, by refrigerating, by adding crushed or flaked ice to the mixing water, provided that the ice is all melted by the time mixing is complete. When we talk about cold weather concreting, experiments in cold weather construction have been carried out by contractors for many years, and much valuable experience has been gained. So for most industrial building projects that are not interrupted during the winter months, there is considered desirable to have the building closed in before the advent of cold weather. But closing in means completing exterior walls and roofs, a long job in the case of large buildings. So it has become common practice to enclose a structural frame with large tarpaulins or polyethylene film, and that added advantage of letting light into the enclosed space. Within the enclosure, the use of equipment such as space heaters or automatic oil furnaces permits temperatures that allow most type of construction work to continue throughout the winter. Here you can see there are a few types. You can see oil burning heater. You can see enclosed hanging scaffold, and you can see the tarp enclosed foundation, how that actually works on the site. So a few insulated forms shown here, and the process of removing part of protective enclosure. So please refer to these images. And let's talk about shotcrete. So the ACI has defined shotcrete as mortar or concrete conveyed through a hose and pneumatically projected at high velocity onto a surface. Placing concrete in this manner is considerably different from the conventional approach in that the concrete can be placed in a relatively thin, high density layer over any surface. And two approaches have been developed for placing concrete in this manner, the dry and the wet process. So, and in both processes, the placing of mix depends on the experience of the person operating the nozzle. And in the dry process, the nozzle operator must add the appropriate amount of water, maintain a correct nozzle angle, and control the amount of rebound. In addition, the operator must have an appreciation for basic concrete principles such as the minimum cover for reinforcement, finish thickness, and surface finish. As in the dry process, material application in the wet process require much the same techniques, except that no additional water is required at the nozzle. So we are moving to concrete joints, and that has already been discussed in chapter 6. We're just gonna take a quick look at these, and those are expansion joint, isolation joint, control joint, and construction joint. Let's take a quick look. Expansion joints are used to allow two sections of concrete to expand against each other without causing damage to each other. The need for true expansion joints is actually rare. So in most instances, the dry and shrinkage of concrete sections exceeds the potential thermal expansion of the concrete in the future. So in many cases, the call out on the plans for expansion joints is an application of an isolation joint. So, and the isolation joints are intended to separate the placement of horizontal sections of concrete from one section that might be expected to move differently. Let's take a look at the control joints, and they are used to control cracking in slabs. So it can be done by placing removable strips or plastic or similar material at predetermined intervals, or they may be saw cut after placement. Construction joints are intended to divide one construction activity from another. So, for example, they're used to terminate a day's placement so that when the next placement occurs, there is a logical location and transition from the older placement to the new. And additionally, it's sometimes necessary to provide load transfer across construction joints, so doweling might be necessary. So let's move to finishing and curing concrete. The treatment of exposed concrete surfaces to produce the desired appearances, textures, or wearing qualities is known as finishing. The procedure to follow depends primarily on whether the surface is horizontal or vertical, and horizontal surfaces are usually exposed and must be finished before the concrete is hardened. Concrete must first be struck off level as soon as it has been placed, which is done by the use of strike-off bars worked against the top edge of screeds previously set to the proper height. So further finishing and then is then delayed until the surface is quite stiff but still workable. Any water appearing on the surface should be removed with a broom, burlap, or other convenient means. Um, so it's not recommended to sprinkle cement or a mixture of cement and fine aggregates on the surface to take up excess water. So this is known as dry shaking and forms a layer that will dust and wear easily or develop many fine cracks due to shrinkage. So here you can see the different tools. You can see short wood float, then magnesium float, broom surface. This is how that is done. Then steel trowel, and you can see how that actually works in operation. There are power trowels as well. And then jointing tool and edging tools are shown here as well. So when vertical surfaces have to be given a smooth finish, a different technique is used. First, the forms must be removed after the concrete is sufficiently strong. The tie holes must then be filled with mortar, or the snap ties must be broken off, and all depressions must be patched. So all rough fins and protrusions must be removed, which can be done by rubbing the surface with a flat emery stone. Next, the surface is washed to remove all loosened material, and at the same time, the concrete is dampened. And then grout is applied to the surface with a stiff brush and rubbed in with a piece of burlap or a cork float that will fill in the pores and small holes. So fresh concrete contains more than enough water for complete hydration, but under most job conditions, much of it will be lost through evaporation unless certain precautions are taken. So, concrete can be kept moist in several days, such as by leaving forms in place, sprinkling with water, covering with water or a waterproof tarp, and sealing the surface with a wax coating. So, when concrete is to be kept moist by sprinkling, care should be taken not to allow the surfaces to dry out between applications. One method of doing is to cover the concrete with burlap or canvas. And we are moving to the hot concrete. So in situations in which concrete is to be mixed in the central plant for use in producing reinforced precast products or for concrete block, it has been found out that under proper conditions, fresh concrete can be placed successfully at temperature up to 175 degrees Fahrenheit. So the primary reason for using hot concrete is that it sets and gains early strength much more rapidly than concrete placed at conventional temperatures. So moderate concrete temperatures of up to 90 degrees Fahrenheit can be achieved economically by heating the mixing water and the aggregates. To achieve the best results, the steam should be injected when mixing intensity is high. And for this reason, countercurrent mixers, which produce high intensity mixing, are often used in plants producing hot concrete. So cleanup of mixing and casting equipment is important because hot concrete sets up quickly. The mixers will have to be cleaned twice a day and conveyors and buckets up to 6 times a day. And we are moving to the last section of the chapter. So that is design of structural lightweight concrete. Structural lightweight concrete is defined as concrete that will have a 28-day compressive strength of more than 2,500 psi and an air dry unit mass of less than 115 pounds per cubic foot, but normally more than 85 pounds per cubic foot. So properties of structural lightweight aggregates, we already discussed that in the previous chapters. So they're usually made from expanded clay, shale, slate, or blast furnace slag, or from fly ash that are normally produced in two sizes, fine and coarse. So the bulk specific gravity for lightweight aggregates is generally between 1 and 2.4. And for any specific aggregate, the bulk specific gravity will usually increase as the maximum particle size decreases. As far as the proportions, proper proportion of lightweight concrete mixtures may sometimes be achieved with the conventional procedures used for normal density mixes in a few specific instances. The variations in rate of absorption and total absorption of moist lightweight aggregates can make it difficult to establish a water-cement ratio accurately enough to be used as a basis of proportioning. Instead, it's found to be more practical to design lightweight aggregate mixes by a series of trial mixes proportioned on a cement content basis. So as far as water and cement content, so concrete made from normal density aggregates with 3/4 inch maximum size will require from 310 to 360 pounds of water per cubic yard. And as far as the cement content, there is a chart showing the approximate relationship between strength and cement content, and it can vary widely depending on the characteristics of the lightweight aggregates. Let's take a look at the entrained air here, and that will be the end of our chapter. So most lightweight concretes contain 2 to 4% entrapped air, but this has little effect on workability and durability, as it's desirable to add entrained air to most lightweight mixes. So trial mixes. Let's discuss that a little bit. So due to the specialized nature of designing lightweight structural concrete mixes, the development of trial batches is better left to producers who deal with the nuances of lightweight aggregates and mix interaction on a continuing basis. And this wraps up our chapter 7. Thank you so much for watching. I will see you in chapter 8.